Hi everyone, this is Professor Fernandez, and this is the last video in this lesson, Module 3. So we've talked in the first video about how to convert between polar and spherical coordinates and Cartesian and back and forth. And we talked in the previous video, Module 2, about how to do double integrals in polar coordinates. So this video closes us off with triple integrals in spherical coordinates. So this is a definition that looks very familiar now at this point if you watched the previous video. It tells us how to convert all of the elements involved, in this case in a triple integral, given in a Cartesian coordinate system, to a spherical coordinate system. So I'm just going to run through what all the elements are here. So we're going to assume that the function that we're going to integrate, the integrand, is continuous on this spherical region. So what is this region? We're keeping things sort of simple here. Theta varies from alpha to beta as it has in the double integral world. Phi is going to vary from c to d, just some numbers, nothing complicated. And rho is the one that's going to vary between two functions. So again, I've referred to spherical coordinates as kind of like polar coordinates in 3D. And we saw in the first module that rho kind of plays the role of r, in the sense that rho is a distance from the origin in 3 dimensions, just like r is a distance from the origin in 2 dimensions. So you can think of this spherical region, this region in 3 space, as the first part being the analog of what we did in the previous video with r going from h sub 1 of theta to h sub 2 of theta. I will scroll up to just remind you of what I'm talking about there. So remember this version of the definition for the double integral, where r went from the h1 of theta to h2 of theta. Similar thing going on here, where rho goes from some function, in this case of theta and phi possibly, to another function of theta and phi. I won't try to draw that because that is a little bit difficult. I've actually put in some drawings over here that I made before I started the video to help myself and you out. But anyway, this is the region that is in many ways the analog of this polar region that we talked about in the previous video. So everything else that happens in this definition is very similar to that double integral in polar coordinates definition in the previous video. I have a triple integral of a function of x, y, z, and I have a volume element that I have to convert, and I have a region E that I now am expressing in polar coordinates. So what happens? Well, let's start with the easy stuff. From the first module in this lesson, we learned how to convert x, y, and z to polar coordinates. So everywhere you see an x, you put in, and I notice that there's a typo here, should be rho sine theta, rho sine phi times cosine of theta. So I will fix that. And then rho sine phi sine theta is your y, and then z is rho cosine of phi. So I'm going to scroll back up here to the actual conversion. Remember, this was from video 1. So there was the x, there was the y, there was the z. So in an integrand, where you have a dependency on x, y, and z, those are the 3 formulas you use to convert it to rho, theta, and phi. And then this is the conversion, all of this over here, of the volume element. It's a little bit more involved. And these are the pictures that I've drawn down here to explain that. So I will do that in a minute. And then the last thing is rho here, we're assuming goes from this function to that function. So that explains these bounds. And we're assuming that theta goes from alpha to beta. So that explains that. And then phi, we're assuming goes from c to d. So that's that integral. Excuse me. Okay, so as in the previous modules video, the only thing left unexplained is the volume element. And I'm going to follow a very similar approach to what I did back there, except this looks a bit more involved. So let me just walk us through it here. This red blob is this spherical wedge that we had talked about in the first module. So what's going on here? So I have started with, let's take these 2 points here of the spherical wedge. So how are these 2 points traced out? Well, your distance rho from the origin, that gets you to this point. And then you are also at an angle phi from the z-axis. So and you're at some angle theta, from the xy plane. But I won't necessarily draw that. And then what do? So now you change the phi angle, so you move this way a little bit to get to that point down here. Great. And then that incurs a change in your angle phi of delta phi. Okay, so now you're down here, and then what do? Well, so now you move theta. So you're down here, and now you move theta a little bit, going that way. Okay, so you do that, and you end up over here, kind of on the back side of this wedge. And then, you could go back your delta phi to end up here in this part of your wedge. So if you've done all that, then you have traced out this back part of the wedge right there. And then to create the actual wedge, now what you have to do is you have to go from any one of these 2 points. I started here and did a little loop that way and got back here, but you could also go the other way and maybe start here and do the loop going that way. Anyway, you go from here where you are and you go outward. So you go that way. So you just take this thing and you just protrude it, extend it out like that. And there gets, you get your spherical wedge. And so when you do that, you are changing the the rho, because you're going further out from the origin. So that is a change in rho, that's delta rho. And then what we're going to do now is we're going to try to find the volume of the spherical wedge. And that's going to be the conversion of dv that's going to give us this portion of the integral. So how do I do that? So I have embedded in here some right triangles. I've tried very hard. Here's the y-axis. I've tried very hard to draw lines parallel to the y-axis that start at the z-axis over here and go all the way to the top corners of the spherical wedge. And I've done that so then we can pop out this green triangle. So now I'm going to focus on this green triangle up here. This one, this one, this one, that one. And I'm going to pop that out. So that's down here. The reason I want to pop it out is because this is rho. This is the hypotenuse of this triangle. That's this length right there. And then this angle here, interior angle, is phi. That's what it was at the very beginning when we started talking about this diagram. And so if I look at then sine of phi, it is the opposite side, over the hypotenuse, which is rho. And that tells me that if I solve for the opposite side in this equation, I get opposites equals rho sine phi. So that is why I've put a rho sine phi there, because that really is the length of that side of the triangle. Great. Why is that useful? Because now we're back to the same geometry with s equals r theta we had reviewed in the previous video. If this length of this line segment is rho sine phi, and I am sweeping it out for some angular inclination delta theta, then the length of this red portion of the wedge is r, quote unquote, theta. S equals r theta. So this s length right here is the radius, which is rho sine phi, it's this, times the angular change, which is delta theta. All right, so now that gets us a really nice result, which is that I have the length of the back end of this wedge, and as I've drawn it, it's the same length over here. So now I can try to find the area of this back part of the wedge, of that stuff, before I change rho to make this other wedge, before I do that. Great. And how do I find that area? Well, this part I know. This is, again, another application of s equals r theta. I have a distance from the origin, this is rho, and it is being swept out this way for an angle delta theta. All right, so this arc length is rho delta, delta phi. Rho, this angle here, rho delta phi. So this is length rho delta phi up here, and this is length rho sine phi delta theta. That's this length here, that's this length here. Great, so far I have a length of my rectangle that is this times rho delta phi. And then now I'm going to create my wedge by just expanding this by some distance rho outward. So that distance, by some distance I should say delta rho, to create a volume. So multiply that by delta rho. And the volume that I get, if I call that a small volume delta V, gets me down to this approximation. And again, as all of these quantities that are finite changes turn into infinitesimal changes, that is where you see we have 2 factors of rho squared. We have a sine phi, and then we get a d rho, d theta, d phi. So that's this part of the volume element. So this is where the volume element rho squared sine phi, d rho, d theta, d phi comes from. And that is what you see up here as the volume element for this triple integral. Great, so at this point we have converted everything. We know where the volume element comes from. This is x, supposed to have a, like I mentioned, typo there, cosine theta that I'll fix. And then this is the y, this is the z. And then we have our bounds here for the types of regions that we're going to be integrating here. Excuse me, so let me show you then how to actually do this in an example. So let me remove all of this so we have space to work on our example. Great. So in this example, we are going to continue with some of the geometry, and we are going to find the volume of another solid. And this one is going to be a lot easier to picture, unlike the last one from the previous example in Module 2. So the solid here is the one that lies above this cone and below the sphere. You might say, how is that easy to picture? And I'll say, well, let's first graph things. So this is a cone. So why is it a cone? Well, if I look at the level curves of this function, let's say z equals k, I get x squared plus y squared equals k squared. So those are equations of circles. If k is 0, in other words z is 0, then I get x squared plus y squared equals 0. The only solution for real values is 0, 0. So I start at the origin. And then as I move up the x-axis, or sorry, the z-axis, I get larger and larger radius circles. So that is why I get a cone for this plot up here. Great. And then the E solid that we're trying to visualize here lies above this cone and below this sphere. Okay. So what is this sphere? Well, let's think a little bit about how to write this in the standard form. So what would I do? I would subtract the z minus z equals 0. And then I'm going to just complete the square. So I would add half of this number squared and subtract that half squared also. And then I just keep the sign z minus 1/2 squared, and this would multiply out to a positive 1/4. So I would subtract this 1/4 equals 0. So that is now my equation of the sphere in standard form, which is great because I can pick out the center and the radius. So this is a sphere centered at 0, 0, 1/2, and it has a radius of 1/2. Right, square root of that number. Okay, so that means that if I go to my drawing, my sketch of where I am, I haven't put any units here, but let's suppose that this is z equals 1, because that is the center of the sphere plus its radius. So the sphere goes all the way up to there. And then if I go the center of the sphere minus its radius, the sphere goes all the way down to here. So this sphere looks kind of like this. Okay? So you can see that the cone is going to, at some point, cut through the sphere. So what we're going to get is quite literally like an ice cream cone shape, like this. Right? So our solid E now has this very nice form where it's got this little hemisphere cap, and then the rest of it is this cone that goes down. And this is the solid. And you can imagine all of this is solid and goes around. So that is our solid region E. And again, this is really going to help us to figure out how all of this works for the next step, which is going to be converting all of this to spherical coordinates. So as I mentioned earlier in the previous videos, it really doesn't matter where you start. So, we're going to have to do a triple integral. And we're told that, again, E is the solid that lies above the cone and below the sphere. Below the sphere. So what we're integrating here is the function, the surface defined by the sphere. That is the function that we're, the surface that we're integrating under to get our volume. And then our bounds are determined in part by this cone. So the integrand for us is going to be the spherical coordinates version of this sphere. So that's going to go here. So I'm just going to write the integrand first in the well, I'm not going to do that because actually I have z's here. I don't want to solve for z there. So actually let's go ahead and convert the sphere equation to spherical coordinates. How do we do that? Remember that in spherical coordinates, x squared plus y squared plus z squared is just rho squared. So that's nice. And remember that z is rho cosine of phi. So I now have rho squared equals rho cosine of phi. Again, this could mean that rho is 0, but it clearly is not. This is not the graph of rho equals 0. Or it means what it is certainly, which is rho equals cosine of phi. And again, this is just the polar coordinates version of the graph of this sphere. So the boundary of the sphere. Okay, so that's what rho cosine phi is. Anyway, so that's what I'm integrating. I'm integrating rho cosine of phi. And what do I do with that? Well, so next thing I want to do is I want to ask, how do I actually get the bottom boundary? Rho cosine phi is just giving me the equation of the sphere itself, but I'm not integrating the sphere itself. I have this boundary, which is the cone. And the cone and the sphere intersect. So I want to find those intersection points so I can help myself create my boundary. So how do I do this? So I can set the, I can look at the equation of the cone first, which is up here, and convert it to spherical coordinates. So I'll do the same thing there. So I will erase some of this and leave some room for us. Now we know that the sphere has spherical coordinates. The expression here is rho equals cosine of phi. And then now let me do the cylinder. So this is square root of x squared plus y squared. Okay. So z is rho cosine of phi. And then x is rho sine of phi, cosine of theta. We're squaring that. And then y is rho sine of phi, sine of theta. We're squaring that. So I have a rho squared in both terms. That comes out, and square root that gives me rho. I have a sine phi in both terms. That gets squared, comes out, and gets square rooted. So I get sine phi. And then I have cosine squared plus sine squared, which is 1. So again, I'm in a situation where either rho is 0, which it's not. Again, that's not the graph of rho equals 0. or I get cosine of phi equals sine of phi. In other words, tangent of phi is 1. There are lots of solutions to these, but remember in spherical coordinates, phi goes from 0 to pi, because phi, as you remember, is the angle measured from the positive z-axis. So this is phi equals 0, this is phi is pi over 2, this is phi equals pi, and then that's it. You start going backwards this way, it doesn't make sense when you draw solids. So we confine phi to 0 to pi for spherical coordinates. So if I am solving this for phi between 0 and pi, I get phi equals pi over 4. That's when tangent is 1. And certainly from the geometry too, the solid that we've drawn here, right, pi over 4 is really the only thing that makes sense. If I get a larger angle, then I'm no longer drawing the cone here. I'm drawing some other phi down here, and I won't get a cone if I go to such an obtuse angle. So at this point, I've gotten my equation of the cone, and if you'll think, remember back or go back and view the video where we talked about spherical coordinates, this was one of the examples, in fact, that I talked about. What if phi is constant? And we talked there about how this produces a cone when you graph it. So the nice thing about doing all this is that we now have information about the bounds in spherical coordinates for this volume. So I'm going to put in the volume element, rho squared sine phi, d rho, d theta, d phi. Okay, and I know what my phi is. So my phi goes from phi equals 0. And when I look at this solid over here, and I'm thinking about it sitting in R3, okay, phi is going to go from 0, which is kind of the top of the sphere, right? And then it's going to come all the way down to this edge, which we have now seen is pi over 4. So wherever phi is in my integral, all the way at the end here, goes from 0 to pi over 4. Excellent. And then theta. Where does theta range from? Well, so if I were to start trying to generate this solid, I would start here, and then I will go down to pi over 4. And then theta, well, so theta, maybe I'll draw it this way. I start at theta equals 0. I go to pi over 4. And then I want to start sweeping it around that way. And I have to go all the way around, right, to sweep out the entire cone. So theta goes from 0. Theta is the penultimate integral bound here. Theta goes from 0 to 2 pi. And then I have to think about rho. So where does rho go from? Well, that's where we talked about the sphere. So rho goes from 0, which is eventually the point down here. Remember we talked about this is the point at the very bottom of the cone, which is included in the solid. That's rho equals 0. So if I draw my representative rhos here, right, it's just sweeping out from the origin. The smallest that rho is rho equals 0. The largest that it is, it's on the sphere. On the sphere. So the sphere in spherical coordinates in this problem is cosine of phi. So that is my upper bound for rho. And then the function that I'm integrating, this is the volume of this solid, and I have already put in, using my integration bounds, all the geometry in the solid. So I'm actually just integrating the function 1. You might remember one of our properties of integrals, that the volume of a region E that you can describe using some coordinate system can be written as a triple integral of 1 dv. And then what you do here is that you put the bounds for the region E. And that is exactly what we have done here. Okay, so I'm going to integrate, my integrand here is 1, even though I'm integrating under the sphere. So you might think that f of x, y, z or something is a sphere. But in fact, we have described the entire region E using these integration bounds. So again, when you do that, you can get the volume of that region just by triple integrating the function 1. So at this point, I've done a lot of work to convert everything to spherical coordinates, to draw our region, and to make sure that we have the right volume element in here. So this is all deliberately choices made by me so that we can focus again on one thing at a time. So, you know, the integrand here is as simple as it can get. So we are now just integrating rho squared sine phi. If I integrate with respect to rho, then I get just rho cubed over 3 sine phi from 0 to cosine phi d theta d phi. So if I then use my fundamental theorem of calculus step, then that is going to give me, I'm going to put in cosine phi into here, and I'm going to cube it. So that's going to give me, I'll pull out the 1/3. That will give me sine phi cosine cubed phi. And then I put in a 0, I'll get 0. So I'm not going to add anything to that integrand. Okay, and now we're back to double integral land. And in fact, it's even easier because we can integrate out the d theta. There is no theta here, so theta just integrates to 2 pi. So I get 2 pi over 3. Integral from 0 to 4 sine phi cosine cubed phi d phi. And now we're back to single integral land. And this one actually is a nice integral in the sense that you can easily use substitute it. So if you let u equals cosine theta, the derivative is minus sine theta, sine phi d phi. And you can use that to write this integral as negative 2 pi over 3 u to the third du. I'm going to write this even though we should convert the bounds if I write it this way. But the idea is that this integrates to u to the fourth over 4, which is cosine to the fourth of phi over 4, evaluated from 0 to pi over 4. Oops, I had a feeling that would happen. I'll just try to zoom in, bear with me here. To pi over 4. Perfect. And then this is, again, something that you can finish off and verify that the answer you get is pi over 8. Which in this case, again, we described the solid E using spherical coordinates. So we were out to find a volume of a solid anyway. So we have found the volume of this solid. It is pi over 8. And in this case, it is an honest-to-goodness volume, not a net signed volume, because we were, thinking about it various ways. We were integrating the function 1, or also, we had drawn the volume that we were going to draw. It's clearly all, quote, positive volume. There's nothing under the xy plane. That was, in fact, one of the things that bounded us. So bounded below by the cone, which lies above the xy plane. Okay, so quick little recap here. When it comes to triple integrals in spherical coordinates, as I mentioned, there was this typo here that I will fix. So you replace x with rho sine phi cosine theta. Replace y with rho sine phi sine theta, and then z with rho cosine phi. Your volume element, the second most important thing, is a little more complicated, but hopefully you can rewind this video and take a look again at how we derive that. And then last thing to mention about spherical coordinates is kind of like what we just did in Module 2 video with polar coordinates. It is advantageous to try to do enough practice problems so you get comfortable with how you should use what form of the equations in Cartesian coordinates you should start from to convert to polar. In spherical coordinates, if you see x squared plus y squared equals z squared, or plus z squared, x squared plus y squared plus z squared, that automatically converts to rho squared. So that is a really nice conversion. Z is another nice one. Z is just rho cosine phi. So if you see those two terms in your integrand or elsewhere in the solid you're trying to convert, I would leave it as is. As happened with the polar coordinates example, if you rewrite some portion of your region of integration by completing the square, doing some algebraic manipulations, it might not be wise to start from that form, even though it might be simplified in some way, to start from that form and convert to polar coordinates. You might want to go back and again look for the sums of squares. Even here where we had x squared plus y squared, which is not anything that's super nice as it is in polar coordinates, which is r squared. When we converted it down here, I kind of erased it, but we got, I believe it was rho squared sine phi. Rho squared sine squared phi, I believe. Or maybe just, yes. Well, after we took the square root, we got rho sine phi. So this x squared plus y squared converts to rho squared sine squared phi, which is, fairly nice. So that was the last tip. Try to look for sums of squares of x, y, and z, or just z alone, or just obviously x or y alone, and that will make your life easier in terms of conversions. Great, so that is the end for this lesson, and again, this has been a tour of double and triple integrals in polar and spherical coordinates, along with, of course, a review of polar and an introduction to spherical. I highly suggest doing practice problems, especially because spherical coordinates is probably new to you. You probably have seen polar coordinates before in Calc 1 or 2 and or in pre-calculus, but typically not spherical coordinates until this course. And it will take some time to be able to visualize things in a way that makes sense in a spherical coordinate brain. So I would come back to this example and try your hand at this. And also the first module, the first video in this module, so that you can get a little bit of a sense again of how basic spherical coordinate graphs looks like. What if rho is constant? What if theta is constant? What if phi is constant? Great, so I'll see you in the next lesson.